Welcome to the section on training an artificial neural network with TensorFlow. Previously, we had seen how with just a few lines, we were able to train this model while making use of this data. This happens to be a sequential model, and it is just one out of 3 ways we could build models using TensorFlow. Let's import TensorFlow. Then from TensorFlow, we import Keras. Since we're working with this data, we import pandas. We have pandas, and then NumPy. So to prepare this data set, we are practically using the same code we had before. And subsequently, we shall see how to make use of TensorFlow's APIs to easily prepare data sets like this. For model creation, we should start by exploring a sequential model. So suppose we have this model we've defined, let's call it model sequential. And then here we have model sequential 1, we add this, and then finally add this. So we've defined model sequential 1, which is a sequential model. We've added this dense layer. So this dense layer is practically the same as a linear layer. Now we want 500 in the output, and here we want 26 in the output. Obviously here we want a softmax, so change to softmax, sigmoid, and there we go. We've built our sequential layer. Now let's look at the second way in which we could also build a sequential layer. This other simple way of doing the same thing that's building the sequential model is by simply piling these models up, or these layers up in a list. So we have this first layer and then this next layer. If you notice, this dense gives way for us to put in this activation. So right here we could do this. So we have activation sigmoid, we take this off. Right here we have activations, and there we go. So we've done the same thing here. So there are 2 ways we could just put out this sequential model. That's by simply doing this, defining the model and calling this add function, and then adding up these layers, or you could directly add up the layers. Now note that we're just calling the sequential, but then it's from tf.keras.model. So we have from tf.keras.models import sequential, and then from tf.keras.layers import dense layer. So we import a dense layer from the Keras layers, and we'll run that. Let's get back to this. We've just built 2 sequential layers. Now let's understand the reason why sometimes we may use a sequential layer and sometimes we may not be able to use it. Now, if we look at these 2 graphs, we'll find that with this 1 year, all these layers have been stacked on each other. So we have this first layer, the next layer, and the next. So they just have this unidirectional path. But then with this other graph, we have, first of all, 2 outputs instead of just 1 output, as in this case. But some of the nodes, like this one, are linked to many more other nodes, and there are also different paths right from the input to the output. So we could go this way, we'll go like this, and we could go this way. This may seem a bit confusing as dense layers are something like this, but you should understand here that in this context we are considering a dense layer to just be one of these nodes. So actually a linear model is just one of these nodes. So right here, this represents 1 node, or right at this represents 1 node, and this other another node. And with the add method, we're basically stacking them up. As we could see here, we have the input, we add a node, we add another node, or we add a layer, or we add another layer. So with this, we see one shortcoming of a sequential model. Now, to create models where the layers are interlinked, like in this graph, or where we have many inputs and many outputs, we make use of the functional API, which is quite different from the sequential model we just built. So let's build a simple model using the functional API. And as the word goes, layers will be seen as functions which take in data as input. So now let's take a simple example of the functional model. What's a bit different here is we have this input as a keras.input, which is defined, and since our inputs are of shape 20,017, we have an input which is defined as such. So we don't actually take into consideration the dataset size. We have this, we define a linear 1 layer, that's the first linear layer, which is basically this layers.dense. Let's take this off. We had defined this already. So right from up, we had defined tf.keras, the layers, we had imported it. We had said from this import sequential, and then from this import dense, but this is not tf, this is TensorFlow. So let's go back to this TensorFlow, run it again, that's fine. So if that's okay, you could take this off right here and take this off. So that's great. Now we come back this way, take this off, and then we're fine. So here again, we have had this intermediary value x, which takes in linear 1. So here we have linear 1, which acts now as a function which takes in the inputs as input. And then linear 2, which is this function which takes in this intermediary output x as its input, and then we have the outputs. So it's kind of similar to what we had here, but with the difference that this functional models can be used when we may have non-linear topologies for our model, when we have many inputs, many outputs, and when some layers have been shared. So it's kind of great to work with under these conditions. Although in this particular case, we just have a plain linear model. So in this kind of situation, we should be using the sequential model instead of this functional model or this functional API. So that said, we have the outputs, and then we define our model, keras.model, we have the inputs and we have the outputs. So that's it for the functional API. Now another modification we could have here is just by calling this x right from here. So we could just call this x right from here and then say this is the output. So we could say output, and then we have this. So we could have this outputs, and then take this and just call in inputs right from here. So we have inputs, and that's it. Now forgetting, we have model, we call it functional. It's only one, so we just have model functional, which is this. Now keras also comes with a way of visualizing our model. So we could do a model.summary. So we have model functional.summary. So run this. Where tool is not defined. Let's run this from up. We have this error. That's actually because here we should have linear 1. So run this again, and then we're fine. So we kind of like able to visualize our model very clearly and easily with this model summary. And then we could also do the same for the sequential model. So we could copy this. So here we have model sequential 1. Run it. Not defined. Let's come back this way, run it. We have a slight error. We take this off, run it. There we go. And then we have model sequential 1. Now, unlike the functional model, here we need to actually build our model or feed it with some data for it to be able to come up with this with a summary. So that's not a problem. We are going to do that shortly. But the result should be exactly the same as this. And here we could count the number of parameters. We have 22,026 parameters. While all are trainable, we have none which is non-trainable. Another way we could define models in TensorFlow is by using model subclassing. Here, this model class is a subclass of this tf.keras.model class. We have the constructor method and then the call method. In this particular example, within the constructor, we actually define these two layers. So we have linear 1 and then linear 2 with these properties. And then in the call method, we'll take in the inputs and then use these layers to generate the output. So like yeah, we could take this as output, like you see output, then yeah, we have the output. So that's it. Now of course we could call this class, so we've created an object of this class model, and then we could call it as a function since we've used the call method. So here we have, let's say let's print out model of tf dot zeros. We have 1 and then 17 as input. So let's print this out and see what we have. So we have this. Now if we look at the shape, inspect the shape, we have this. So the output is 26. Now if we have something like this, see that this actually still works because with the dense layers we don't have the input and the output. So for the dense, it practically just gets the input from what it has here. So like this case, no matter what you put here, you'll always have this output because we did not define this to be say 17 this and then here 500 as we had seen previously. Now let's try to modify this a little. We can define our own linear layer instead of just using this dense layer. So let's say we have this linear layer. We're having this class, which is a subclass of the keras.layers.layer class, and then we have the constructor, which has these parameters, and input as number of inputs and number of outputs. So recall that the linear layer we had been building before previously actually had something like this. We had linear, and we could say for example 17 and then 500. So there's always this precision of the input and the output. So suppose we're building that kind of layer. In that case we have number of inputs, number of outputs, self, number of inputs, and self, number of outputs. Now it's interesting to note that whenever you're building your own layer, that's you're not maybe using already manufactured layer by TensorFlow, you have to define the weights and then the biases in the build. But with the difference that you're not bothered about defining what happens in the backward pass. That's when we're finding the partial derivatives of the loss with respect to the different weights and biases. Here all you do is just define in this call method what happens in the forward pass. So that's why here we have the inputs, as we could see, times that's this matrix multiplication. So we could actually replace this with tf the matmul of this. So this is the same thing. We have this plus self.biases or self.bias. So actually here we're just interested in knowing what happens in the forward pass, and then TensorFlow uses autodiff module to automatically calculate the different gradients. So this is kind of like a template when you're building your own layer. So we have defined this, we've defined the call, and then obviously we have to define the weights and give it some parameters. As here we have a weight and then the bias. If you notice, they are both created using the self.addWeight. So here we have add weight and we have add weight. So this is gotten, or this method is gotten from this class. And then in this method we'll define its shape. So it's important to define the shape of the weights. So yeah, obviously we have the number of inputs, number of outputs, and then for the biases we just take the shape from the number of outputs. We've seen this already. We have the initializer and we'll say whether it's trainable or not. So if let's take this true and this true. So that's it. We've defined this linear model or this linear layer. So yeah, we could take this linear and then here we have this linear. So now we have this, we'll take this 17 and then here 526. Take this off, doesn't take this into consideration. Take this off because it's actually a layer we are creating by ourselves, so it doesn't automatically come with the activations. Now we have that, we have run this. Yeah, we could test this out. So run this and run this. We have an error. Now look at this, we have this error right here, and that's because this doesn't match. So let's take this to be 17 and there we go, it works. So we see that it actually works only when we have this at 17. And that's why the dense layer of TensorFlow already comes with a way in which we don't actually bother on about the type of input we have. So let's change this and let's modify this slightly such that we just have what we have here. So let's consider that we have this. So let's create a linear layer which just takes only this. So in this we just have the number of outputs, so we don't bother much about the number of inputs. Could take this off. There that goes. Now this is the input shape. Note that this input shape automatically is gotten from the kind of input we have right here. So if this input shape, like since we have this as input, it means the input shape will be 117. So in order to collect the 17 or to collect whatever input, so whatever input value we have here, so whatever input value we have here, we could get it by using input shape, but from its -1 index. So here we have input shape -1. There we go. So we have the outputs, we have here the outputs. That's it. We have this input shape which we defined and we just got it from here. We have the outputs and that's fine. So let's run this. Then here, whatever value, we now put say 17. Let's start with what works first. So we have that right, modify this, and I will still have the same answer right. So what's to be understood with this is that this is kind of like a template. So anytime you want to create whatever layer, so you want to create a layer new, and then you don't have it handy with TensorFlow. So TensorFlow doesn't come with a layer and you want to create it. What you just need to do is to have this build, you have the call, and then you have this init methods. You define this parameters, and then you define also how the forward pass goes on, while TensorFlow takes care of the backward pass. You have to recall that in the backward pass, if you have any particular function you want to define that doesn't come handy with TensorFlow, you could use this tf.custom gradient decorator. Also, when working with TensorFlow and building models, TensorFlow automatically generates a computational graph like this one. In this case, we find that we have two computational graphs, this first dance and then this other dance. So here we have the input which we had seen, and then we have this dance and this. Now, if we try to look at this a bit, since the dance layer takes in just the input, so here we have this question mark. The question mark is like the data set or the batch size. So we have 17, and then it gets into this first dance layer, and then for the next dance layer, the input is this question mark times 500. So we have this input into the dance layer. Now when we double click here, we have this. We could pull this out, reduce it a little bit, and we'll see exactly what's going on in this dance layer. So we see how this dance layer is represented by this graph. So here we have this matmul operation which takes in an input and then multiplies it with the weights. Now see that this read variable actually here gives us this. So here we have the weights. Could take this, reduce this. We have the weights, we have the inputs, matmul, and then plus the bias. So let's drag this. So you have this plus the bias. So this is the output of matmul, and then we have the sigmoid activation. So there we go again for the bias. We just have an add, so just an addition right here. Could take this, and then going to the next, we find that we have something similar. Well, we have this. We read the weight, matmul, and then bias. And later on the softmax instead of sigmoid this time around. So this kind of tells us that anytime you create a model, TensorFlow creates something like this. So we have this, but then TensorFlow has two modes, that's the graph mode and then the eager mode. When TensorFlow was first built, it was actually built on the graph mode. So it came with this graph mode, which from every model builds a graph data structure. And this graph data structure is advantageous in that it can be used in other environments other than this kind of environment where we have a Python interpreter. So it means you could take that data structure and then reuse it even when you don't have a Python interpreter. So this could be used in mobile phones and many other embedded systems, browsers, and other systems you could think about. Also, when doing distributed training, working with a graph data structure like this actually makes training quite easy, as a bigger computational graph will be broken up into several parts. And then we also have a more optimized code. But then these advantages come with some disadvantages, which developers didn't very much appreciate at the beginning. Although now we have a more intuitive TensorFlow tool which we work with. So by default, at first we had the graph mode, but now by default the mode is an eager mode. Now this eager mode permits us to work without necessarily converting our models into data structures or into the graph data structures. So this makes us write code as if we were just writing Python code. So with the graph mode, you kind of like wrote code which was tailored for this graph mode. So the code wasn't just bare Python code, but developers felt like they were learning another programming language, which was TensorFlow, because it had its own syntax. Now we don't have those problems anymore. You could write code as if you were working in Python, and TensorFlow takes care of automatically converting this into whatever mode, or more precisely into the graph mode. And also another big problem faced by developers, apart from the fact that the code wasn't highly intuitive, was also that when doing debugging, error management wasn't very easy. Let's take this little example to illustrate the difference between the graph mode and then the eager mode. So here we are in the eager mode, since by default when we define our functions or when we write code with TensorFlow, we are in the eager mode. Now before continuing, just note eager is like to say you are in a haste. So you are in a haste, and then graph mode is already for production, or it is actual use. So now when you are still developing, so when you're still developing a product or developing a prototype, there are obviously some changes you want to make. So you don't always want to convert into this form, this graph form, which will make you spend much time debugging. So that's why it's preferable to work in the eager mode initially, such that you could debug your code. Your code also feels like Python code, and then you could advance more quickly at the beginning. And then when you're done with prototyping, or when you're done with developing the model, you can now convert this into a graph mode so that it could run faster and better. So right here we have this function seek, which we have defined. It has a threshold. Now if x is greater than the threshold, s is 1, the output is 1. If x is less than negative the threshold, the output is 0. And in any other case, the output is the sigmoid function. We also have defined this gradient function. We see how here we are able to use if else statements, and also we'll be able to use loops as if we're working in Python. That's because here we're practically the eager mode. Now run this, and then let's print this out. So let's print this tf.autograph.toCode actually converts this into the code that TensorFlow should receive when you're working in the graph mode. So if we do this, we find this code. Now if you notice, we have this if body 1, and then we also have this else body 1. In fact, the code looks quite unintuitive as compared to the kind of Python code we used to write it. Now going back to the function, we had this, which was with this decorator. Now run it. Now if we want to convert our code to all Python, we could define this variable tf.variable 0.0. Take this off. We have this trash. So we have trash.assign tf.constant, which is this. This is off. Then here we have s.assign. So this assign is the same as saying s equals, and it's actually used when dealing with variables. So in this case, since we're having a tensor right here, we should normally not use this. So this is equals, and then take this off. So here we have s.assign tf.constant 1.0, right here f.assign tf.constant 0.0. Now this assign has other forms like assign add, assign subtract. So right here we could take this, and then here we could say assign subtract. Now let's do it separately so you see exactly how it works. So here we have this variable, which is say 4.0, and then we have s.assign add 1. So assign, sorry, this constant 1.0. So we add that tensor, and then we print out s. So we print this out. This error, we find that it takes the value 5, so this has been added onto it. So it's just like saying s equals its value plus 1. That's the rule of assign add. Now take this off. See that it maintains, it becomes 4, it becomes 1 actually, because this s equals 1 now. And then if we take assign subtract, it's actually assign sub, not subtract. So yeah, we'll take this off, assign sub, yeah, assign sub, run this, you see it gets the value 3, that's 4 minus 1. So this shows us exactly what's going on here. Now we have this is actually constant. So we've defined the threshold, define this, define this, define this, modify this to assign. So here we have s.assign, assign of this, then we'll run it, and that's fine. So we have now called this seek function. Also, let's cause an error right here and see the difference with the graph and then the eager mode. So here we're taking this integer, it's gonna give this error. So we have this, has the tab this and all of that, but it's expected to have this kind of values. So see the trace we have. Now let's modify this, let's take this off and kind of appreciate the difference. So we find that with this error, it's quite easier for us to trace and know exactly where there's a problem as compared to the previous with the graph. So we have this, run it, we'll see this. So it's quite longer. And then we check on the tracing. So here we have print. So suppose you have on this model and then you want to print out every time, check the values at this point. Now we have done this, then let's take this off, say for I in range 1000, we're gonna have call this seek 0.2. So let's run this. Now we have check the values at this point, that comes up only once. Now if we take this off, see you have checked the values at this point, which comes up 1000 times. So when it comes to tracing, the graph mode is more appropriate, as if you have to train a very large model and that you have to be printing all these values every time you're doing the train or for each epoch, then you'll notice that your code or your training is going to take much more time as compared to if you just have to print this or trace this just once. So depending on what you want, you could always put this or not. So let's run this again. We'll see how this comes out with only once. And then another common error is to go out of TensorFlow. So like here, if you define this function, you go out of TensorFlow, you just use the numpy, and then let's run this. And then when you want to calculate gradients, you have here, you see that you have an error. You've been told cannot convert a symbolic tensor to a numpy array. So always avoid doing this. Always work in TensorFlow, run this. See that this problem is solved. We've just described 3 ways of defining models with TensorFlow. In order to move to graph mode and speed up calculations, we just simply add here, add tf.function decorator on this call method. And then we convert our data set into tensors. We convert them using the convert to tensor method. Then we cast this so that they have this data type. Then TensorFlow gives us the opportunity to regroup this data set made of X and Y as one. So here we have our training data set, and then we could shuffle our training data set. For the buffer size, it's advisable for it to be as large as the data set. And then we have this batch where here we get the batch size. So basically this is the batch size, and then we shuffle with this method. So with this we could print out our data set, and then we define a number of epochs. So run this, we have this batch data set, the shapes, as you could see, and then the types. And once this is done, we set for training. And for training, we define the loss, which comes already with TensorFlow. We have the optimizer, which comes, and then the metric, which in this case we're going to be using the accuracy for measuring how performant our model is. So here we have the categorical accuracy, we have SGD, and then we have categorical cross entropy. Note that you have to import this at the very start. So here we have done for the SGD from TensorFlow.keras.optimizers, we get the SGD. From TensorFlow.keras.metrics, we have the categorical accuracy. From TensorFlow.keras.losses, we have the categorical cross entropy. Now this has to be imported for us to just call it as we just did right here. So once we have this, we can now get set for the training step. For this training, we have this simple function which does a training, and you should note that this function is quite similar to what we've seen already. It's basically a computational graph, and we're just trying to record the gradients as we go through that computational graph, and then calculate the partial derivatives with respect to each and every of these gradients, and then finally optimize the weights. So it's kind of what we've seen already. So here we have this width TF, the gradient tape as tape. We have the model output, which is equal to the model. That's the model takes in X. The training is true because we're in training mode. And then we calculate the loss, which is getting from the CCE loss that we have right here. That's the Y, and then the model output have been compared to get the loss. And then we compute the gradients by taking the gradient of the loss value with respect to the model's trainable weights. Note that not all weights which make up the model or which are part of the model have to be trainable. So here we have to specify that we want this to be calculated with respect to the trainable weights. So it's kind of similar to what we have seen right here, where we had all this, and this now is kind of like representing the whole model. And then we had this G. Now this G in our case is the loss, and then A was a particular weight we wanted to calculate this partial derivative. So right here we are calculating the derivative of G with respect to A, and then here we're calculating the derivative of the loss with respect to the different weights. And once this is done, we simply optimize those weights. But to optimize those weights, we have this apply gradients method. We have the grads. Now this grads represents, actually normally this is gradients. So we have those gradients, which we just calculated right from here. And then we have the model weights. So if the optimizers SGD, in this case, we're going to be having say model dot, say we're just going to have a weight. So let's call it weight. Suppose we have many weights, so say weight 0 minus gradient 0, or rather weights. So here we have weights 0 equals weights 0 minus learning rate times gradient 0. So this step is actually doing this in the case of SGD. So we'll take this off. And then we go straight to the train accuracy. That's we update the state of our train accuracy for this one training step. That's by taking Y and then the model output. And then every time we simply return the loss. So we return the loss, and that's it for this training. Now once one training step is done, we could repeat this for several epochs. So for epoch in range epochs, that's for 5,000. Let's start with 5. For example, we could have for step, and then this is what we had initially, or rather this was a training data set that we had developed from here. This enumerate permits us to go through this. So we have the steps for each and every step, and then we have this. Now let's print out this, the size of this, so you see clearly how this batch size actually comes to play right here. So if we print this out, we could say print x and then y batch string dot shape. So run this. Oh, let's interrupt this. Okay, so you see that you have this 20,017. Now let's modify this. Let's suppose our batch size is only 20. We run that, we run this, and we run this. So you see that it actually changes right here. So this will tell us that basically from this we could modify the batch size very easily. Okay, that said, we could take this off. So here we go, we have this, we take the loss. So basically from this training set, from this training step, we actually had this loss, which was outputted, which is what we have here, and then we print it out. Then we have this train accuracy that we had calculated. So here we have the train accuracy, and then we reset the states. So from here we could print out train accuracy, because this permits us to get the results that's for each epoch. So we could print out train accuracy. Now this loss, there's a little error right here, but let's just print this out first so you could appreciate the results we have. And so let's print out the loss in this epoch is equals loss, and then right here we have the accuracy, and this epoch is equals this. So that's it. This here is the train accuracy result. So there's it there. Then the model is equals the custom model. So instead of just working like this, we choose a custom model such that later on we could choose model functional or model sequential depending on what you want to use. That said, could go down. We have this, and then let's run this. So we'll run this, and we can see the loss. We have this loss value which is dropping, and the accuracy is increasing. So training is looking fine. After training the model for 5,000 epochs, we have an accuracy of 91% and a loss of 0.321. We could also speed up training by adding the TF function decorator right here. So we have this TF function decorator added here, which can permit us speed up the training. So let's take, for example, 5 epochs and run this. So we see that it just worked just fine. So all we need to do when we want to work in graph mode while doing training is to add this decorator right here. In this function, which takes in the inputs to compute the model output, and then computes the loss based on the model output and the expected output. So we've just seen how to train a model using TensorFlow. Nonetheless, there exists an easier way of doing this. See, we have this, we've defined a model. In this case, we've chosen model functional, which is one of the models we had here. We could even take model custom or custom model and then come back to use model functional, so that you see that we have the same results. So we have custom model, and then we could summarize the model. For now, since we're using custom model, we may not want to summarize that. We compile the model, and then we fit the model. So this is model. So we just have this. We fit the model based on the training data set and then the epochs. So we see that instead of going through or instead of doing all this, we just have to do maybe just this 3 lines. But you should know that everything going on through this model.fit is practically this. So this is what is contained in this model.fit we call it right here. So let's run this. We have the results. So we kind of have the loss, which is dropping, and then the accuracy. Then let's take the other model. So let's take model functional. Run it again. Not defined. Go right up. Let's run this model, the functional we had from here. So we had this. We run it. Then we see how accuracy is increasing while the loss is dropping. So we could take this to say 1,000. Run this again. Now over 1,000 epochs to see how the loss drops while the accuracy increases. So this was just to show you how you could use model.fit to train a model without necessarily getting to go through all the steps to understand how automatic differentiation works and then compute these gradients and optimize the model by hand. Nonetheless, it's important for you to understand the two methods and then know when to use which depending on the kind of task you're working with. And with this, we've completed the section on building an artificial neural network